Can't say that. Can't say that on TV. Things you can't say on TV. Look it up. Don't really. It's George Carlin, but it used to be that, but it's not the case anymore. Actually, that's so funny. You guys have no idea what I'm talking about, but I'm going to talk anyway. Used to be the case. There was a skit with George Carlin. He was a comedian. You don't remember him. Anybody ever hear of George Carlin? No one. Okay. Well, he was a comedian, and he had this skit where he said the 7 words or 10 words or 9 words you can't say on TV, and then he would say them all, and that was funny. Like everybody laughed because he's saying bad words on TV, but it wasn't really on TV. It was like HBO or whatever. But now, I'll bet you, I haven't watched this skit in ages. I'll bet you 9 out of 10 of them you can now say on TV. It's funny because you watch anything on cable, and certainly if you get HBO, there's like no holds barred. But anyway, I'm not just saying. I'm making a comment. All right, properties of matter. That's what I want to talk about now. I'm going to divide properties. I want to divide properties into 2 different kinds, and basically, the first ones I want to talk about are the ones. It kind of seems weird. I'm going to talk about 2 different kinds of properties. You may have heard physical versus chemical properties, and you might think to yourself, well, this is chemistry class. We're going to spend most of our time on the chemical stuff. Actually, we spend most of our time measuring physical properties in this class. Even though we're doing chemical reactions, what happens is there's usually a change in physical properties. That's what tells us there was a chemical reaction that went on. And that's the things we can really measure. All right, so you're actually going to have to learn more about the physical properties than the chemical properties. Now, let's talk about that. I first want to see if you can give me some without me giving them to you. So I'll start with just a little definition of them. And then I'll see if you could tell me some of the things that you would consider physical versus chemical properties. Okay? Physical properties can be observed without changing the identity of the substance. All right? Now, I want you to keep that in mind when I ask you to tell me something about these 3 graduated cylinders. By the way, here's a new name for you. Told you I was going to use these demos to help get you guys familiar with the equipment and the techniques you're going to have to use throughout the year. Well, here are, this is high enough, probably not, a little bit higher. Here are 3 graduated cylinders. These glass things are called graduated cylinders. You usually don't put solid things in them like I have here, but I have some solid things in there. Let's see if I can get a little closer to the camera here. It's right in the way of that thing. Here, close enough. All right, I got 3 things in there, but it needs to get a little bit higher for the camera. Won't you smile for the camera? Another song. I think that was Steely. No, it wasn't Steely Dan. Maybe it was Steely Dan. I don't know. Never heard that song before, I'm sure. All right, got 3 things in there. I want you to tell me some physical properties. And this is a good opportunity. I usually use this opportunity to try to start learning your names. I'll write some of these physical properties down. All right? It has to be something you could observe about these guys without, actually changing the substance itself. And here's the key. This is going to be a thing I'm going to really hammer you on in the early labs. You've got to be specific, but you can't assume anything. Can I be specific without making an assumption? So, what would you tell me? Let's call on some people randomly here, because this is not questions like, what's the square root of 9? What's the square root of 9? Yes! But, it's not really a hard question. It's just, how would you describe, what's different about these guys? Give me a name of something that's different about these guys. Veronica.
Amount.
Okay. That is a great example. The answer was amount. That's a great example of something that is correct but not specific. Amount. Specific. Give me something specific about the property. What do you think? Whitney.
Size.
Size. Still not specific. Still not specific. See, I'm glad we're doing this. I always do this. It seems like such a silly exercise. Yet, these are the kind of answers I get, and I really hope to get these answers in the next class, because what happens is if I get the right answer first, everybody would have thought, well, I could have written size or I could have written amount. No. Again, look at these. Again, think. Keeping in the same theme as size and amount, can you be more specific than size or amount for these guys right here?
May I have your attention,
Hold on.
please, homeroom teachers. Please send your attendance down to Mrs. Maylock, the Skyward System
Does anything work this year? How about B lunch yesterday, huh? Was anybody in B lunch? Woo! That was nasty. I had to leave money with the custodians to pay for my food because I couldn't wait in line. I had a class. You guys just got to go late. I can't go late. All right, keeping that in mind. How else could I describe the amount that's in there? Chase, specifically, what could I do to this? Well, all right, the number, I guess. All right, but in chemistry, you can't imagine that being used. That is correct, and that is more specific. But what's a better one, you think, Faith? Okay, there's a great. This is amazing. We're going through every possible wrong answer, and we're getting closer every time. She said weight, the weight. In science, in chemistry, and most in physics, we don't say weight, and we'll see why later on in this chapter. We'll talk about the difference between weight and mass. It took us that long to get one right answer out of a class of 25 honors students. Wow, that's amazing, isn't it? But yeah, don't write this down. Please don't write it down. I'm going to actually have them all come up nice and neat. All right, but let's write mass down. Okay, I'm just going to write mass down. Yeah. Mass, I could put it on a scale and I can weigh them. I can see which one has a greater mass. That would be one specific way to tell these guys apart. And it would be a physical property because if I get the mass of this guy, he's still that guy. I haven't changed him in any way. Whew. 5 answers. 5 people took. I'll get through the whole class at this rate. Give me another physical property that's different between these guys that I could measure about these guys. What do you think, Kenneth?
Color.
Yes, absolutely. Color is a physical property. Color is absolutely a physical property. It's something I can see that this guy is, what color is he? Like brownish. This guy's clear. This guy is silvery. Okay, absolutely. Very good. Color would definitely be one. Now, you might say, well, how do you measure color? Well, in a number, you can't really measure, but I'm not talking about that. You don't have to be able to measure it. We're going to talk about properties you can measure and some properties you can't. All right? But color is clearly a physical property. I can tell its color without changing its identity. It's a physical property. What do you think? Kendall, another thing about these guys.
What about, like, what it's made of?
All right. Great bad answer. I love this. And by the way, nobody should get, I guess I start off with this and then people get kind of scared about answering because I'm always looking for wrong answers and they think I'm calling on them. I do. I want wrong answers. What it's made of. For example, if someone had told me, well, this guy's copper. Somebody eventually would have said, this guy's copper. That's an assumption. That's an assumption. I don't really know that that's copper. It may look like copper, but I don't know it's copper, number one. Number two, she said what it's made of. Well, what it's made of, I'd have to do something to it to find out what it's made of, probably, maybe even change its identity. That's not necessarily a physical property telling me its identity. That's an assumption telling me its identity. I'm just trying to describe it. I'm just trying to, you were at, like a policeman, came into a scene of the crime, and you make no assumptions, but you're trying to describe the person or the thing that was on the table that may have been the murder weapon. He would want to know how, the size of it, whatever. You want to know a lot of things about it, but you can't assume anything about it either. You can't make any assumptions. So, no, I can't write down what it's made of, its identity, because that would not be a physical property. All right. What do you think, Peyton? What else is different about those guys?
Shape.
Shape would be. Now, shape would be something that will be difficult to, and again, you don't want to write these down because not all of these are necessarily going to have as examples. Shape would be something that would be not very specific, right? So, for example, I could talk about the shape of this versus when I do this to it, right? I don't know if you can see a paper through this. All right, its shape is now different. But how can I be more specific about what can I measure about this paper as I change these things about it or rip it in half? What can I measure about it? That would be a much more specific way of observing a physical property about this piece of paper. And I can also do it about these guys, just not as easily because they're kind of in a container. What do you think? Stone?
Density.
Well, that is going to be one, but no, I'm sticking with this one. When I do this, or this, what's different about this piece of paper versus this piece of paper, or if I ripped it in half?
Folded it.
Well, all right. Now what's different about it between this one and before?
You're changing
It's
structure.
no. It's hard. What could I measure that would be different about this piece of paper than this piece of paper? And Justin. Okay, he said area. You're actually getting to a calculation. Very good. But let's break area down into something even smaller than area. In order to get the area, what would you have to measure? Anna Louise H. Rivenbark.
The dimensions.
Okay, what about the dimensions?
The length.
Length! That's the word! Look how long it took to get that word. That was like 6 people. Length. Yes, we can measure the length. This is going to be a long day. Yes. And by the way, my point is, I actually have a point to all this. The things that you're saying, you're noticing, I'm not accepting on the test and on the labs. I can't accept things like, amount and size. Okay? It has to be specific. And you will have instruments to be able to measure these things. You'll have a ruler. It's in your drawer. When you go back there next week, there's a ruler in your drawer. You're going to use it often to measure the length of something. You have scales. We already showed you how to use that yesterday. Scales back there at everybody's table. You're going to use them to measure the mass of things. Let me ask you this. I told you these are called graduated cylinders. What do you think? I told you I don't normally put solids in here. I usually put liquids in here. What do you think I'm measuring if I put a liquid in there? Autumn? The volume. That's another thing I can measure about it. Now, I kind of led you down that one because I didn't want to spend 20 minutes answering 500 questions again. But this is a good exercise because I don't think there's anybody sitting out there who doesn't think, well, I'm smart and I could do this. This is so easy. He's going to write down a definition. He's going to write down a couple of examples, and bam, I can spit it back to him on the test. Absolutely true. You all are smart enough that if I had just given you this, and by the way, density was other. I heard other ones that were true. Area. All these are correct, and I'll put a few up here. You can start copying them down. All right. These are just some examples. Okay. Everybody here could memorize those things and more. Everybody here could know the definition and memorize the definition. But everybody here, it's obvious to me now, that would have made mistakes on the lab. Because when you went to write your observations, you would have said stuff like amount and size and the identity of something as a physical property, when in fact those are not. At least they're not specific enough, or they're making an assumption. All right, and you can see that. That was my point of getting all those wrong answers, and I hope I get as many wrong answers. It's a class this big has disadvantages. When we go back in lab, it's hard for me to help everybody at once, and even when we're working on problems. But it has advantages in that with all you guys in here, I'm going to get all the mistakes, and that's a good thing. The best way you learn is by listening to those mistakes and then not making them. As a teacher, anybody thinking about being a teacher in there, you don't have to raise your hands. If you're thinking about being a teacher, I will guarantee you, you will not be a good teacher your first year. It doesn't matter how nice you are. It doesn't matter how good you are. It doesn't matter how much you love the children. It doesn't matter what time you stay up till late at night preparing your classes. You won't be good because you can't anticipate the mistakes that kids are going to make. You just can't. And even in a class, like if I had this class like my other one's only got like 10 people in it, if they don't come up with those mistakes for me sometimes, I'll forget to mention them to them. And then sure enough, come the first lab, come the first test, they make them. That's why it's good to have 25 people in a class in some cases, because I get all the mistakes out of the way. I mean, somebody in here is thinking differently than me. I can't think like every one of you guys. All right, and so I'm glad to get those mistakes out of the way. All right, let me move these guys out of the way. I can measure all those different things about this guy: the volume, the density, somebody mentioned, the color, the shape, temperature. That's another one we're going to use a lot. Even stuff like usually comes up as texture, but the big ones we're going to use are going to be volume, mass, length, and temperature. Those are going to be the biggies. We're going to do those most of the time, and those are the ones we have the instruments for in the back to do. All right, now let's compare that to chemical properties. Okay. Chemical properties, obviously, I could define it partially at least as something that can't be observed without changing. I have to change at the end of the substance. All right, but I'm going to say it a little bit differently. That's correct as well. But it depends on how a substance reacts with other things. And this will change the identity of the substance. So I have to do something to it. Now the crazy part is, as much as you can come up with tons of examples of physical properties, you're going to have a hard time coming up with things that would be chemical properties, I'll bet you. I'll let you try. But there aren't going to be as many that you're going to know. That's my guess. Now, let's just go back to what I did to this paper. When I ripped it in half, I was changing the length, I was changing the area, I was changing other things about it. Some things stayed the same. We'll talk about that, fundamental versus physical properties versus derived and stuff like that, and intensive and extensive physical properties. We'll talk about some of those things. But one thing that didn't change is its identity. I ripped this up as many times as I want to. It's still paper, right? Can you give me something I could do to that paper that would test something, a chemical property of it, but I would no longer have paper anymore? What do you think? What do you think, Samantha? No, Santina. If I burned it, yeah. That would determine if it was flammable or not, correct? That's probably the number one chemical property you know of, flammability, right? And there aren't very many other ones you could probably think of. As the year goes on, you'll learn a few more. For example, whether something's an acid or a base is a chemical property. We'll talk about that later in the year. And just its reactivity. Does it react with certain things? That's one of the ways we are able to identify stuff is based on how it reacts with other things. And so that's not it's a very generic thing. I can't really give you specifics on that because sometimes it will just react with metals, does it react with oxygen, does it react with water, and all those things are important in identifying the chemical properties. So I'm only going to list a couple here, not like there are way more physical properties that we're going to measure. And like I said, it's kind of weird. Class is called chemistry. We're going to spend most of our time measuring physical properties, not chemical properties. Although you are going to burn things, and you are going to measure pH, and you are going to measure reactivity in a lot of different labs. Okay. Now, again, I hope you see how my class is a little bit different, even after this is only the third day, right? And we have a lot of demos to show you in this next part. Class is different because, I generally spend a lot of time talking about one single board and do a lot of other questions and demonstrations for you. It's not like I expect you to, can you see it? Can you visualize yet where I'm going with this? Like I said, there are mistakes you would never know you were making about these things, all right? And you would start to make them if we didn't go over all that stuff. All right, let's go physical versus chemical changes. We're going to talk about physical versus chemical changes now, because remember the definition of chemistry was, this title of this chapter was matter, energy, and its changes. Well, we talked about energy, we talked about the properties of matter. Now we're going to talk about what makes something a physical versus a chemical change, and I want to start with physical changes. I've already shown you one, just ripping up a piece of paper. There'll be easy ones like that, and then there'll be harder ones, and I want to talk about those a little bit too. Then we'll stop, have you work on a few problems, and the second period I want to do, the second half of this period, the double period, I want to do a lot of demonstrations and show you and identify what makes something a chemical change. So let's just talk a little bit about physical. Won't take you very long, and we'll take a little bit of a break for some of the problems you're going to do in questions because you didn't get a chance to do some of these yesterday. All right. In a chemical change, as we've already kind of said, there's no identity change. No new substance is formed in a physical change, that is. And here I'm talking about the identity of something, the actual makeup, the chemical structure of this. Ripping up paper doesn't change it from paper, it's still paper. Okay? But burning paper turns it into something completely different. Turns it into carbon and carbon dioxide gas and a little bit of carbon monoxide gas. Okay? It no longer, even some water is given off, believe it or not. There's no change in the identity if I'm simply ripping this up, crumbling it up. Those are easy things, I think. Most of you understand that. I can also reverse the process to get back the original substance. Now, once again, if I were a very bad teacher, if I just gave you these two things and went on to the next one, and let me tell you why, as you write that down. If that's all I said, if that's all I were saying, what would you say to me? Could you answer these following questions? What about boiling water? Looks like I got a new substance there. What about a magnet? What about like that magnet we use the other day to test something? What about electricity, conducting a current? Is there a new substance formed? A lot of you guys might think, yeah. In water, if I boil it, looks like I had water before. It boiled away. Now I don't have any water. We must have something new formed here. And same thing's true for magnetism or electricity, for conducting electricity. They're all examples. They're all the tough examples. They're all the problems that you're going to see. That they're all still physical changes. And that's because of this second one especially kind of points that out. If I evaporate water, if I boil water off, it's in the air. I can't see it, but it's still water. And how do I know that? What could I do to that water after I boil? What could I do? What's the opposite of evaporation? Everybody knows this. Cecilia. Yes. So I can get my water back. I can reverse the process by a physical change and get that back. So there are some guys that are confusing. And I purposely list these here because, in elementary school and in middle school, if you did physical versus chemical changes, remember, you did. You've seen physical versus chemical before. I know you have in all your classes. Not all of them, but in most of your classes. They were going to ask you stuff like ripping up a piece of paper or burning a piece of paper, and it's obvious which one. But I'm not just going to ask you those easy ones. I'm going to ask you stuff like dissolving stuff in water. Dissolving sugar in water. Sure looks like the sugar went away. Sure looks like it's not there anymore. I can't see this white crystal anymore. It's just the water I see. How can I reverse the problem? What can I do to get the sugar back if I dissolve sugar in water? What can I do? Cindy?
You could boil it.
Yeah, and what will be left after I boil all the water away? The sugar will be right back there on the bottom, right? I can reverse basically the process. Same thing's true with any phase change. I can reverse the process. I freeze something, I can melt it. I melt something, I can freeze it. If it's a reversible process, and I actually don't get anything new. And by the way, going back to the dissolving, so that's sugar and water, right? Did those two guys still maintain their own properties? In other words, if I drink one packet of sugar in water, or if I just eat the packet of sugar directly, don't I get the exact same number of calories from that? Sure. I don't reduce the calories by putting it in water first. All right. Conductivity, magnetism, these are the weird ones. These are the guys that we often get wrong. And the phase changes, I'm going to ask them in different ways. Definitely going to ask these guys in different ways. All right. For example, I know the book, one of the questions tonight in the homework today, in the homework you're going to do in a class, will be like the formation of clouds. And people are going to want to put chemical down. They came out of nowhere. They weren't there before. Something new. What is the formation of clouds just an example of? Condensation, right? So it's just a phase change. So you've got to be careful of those. They're going to be on the test. They're going to be on the worksheets. And they're going to be the homework tonight. All right, so these are the tough ones. You didn't get conductivity, phase changes, dissolving in your elementary school classes. You got crumbling up cookie, or baking a cookie. Well, there's a good one. Is there a chemical reaction that goes on in the baking process? Yeah. All right, that's a chemical change. But if I just crush a cookie and take a hammer to it, that's just a physical change, okay? All right, lastly, the chemical changes. And these, again, I'm going to go through quickly because next period, the second half of the double period, we're going to do the evidence of a chemical change, which is going to involve a lot of demonstrations over there, okay? All right, chemical change. Or, what's another name for chemical change? A reaction, a chemical reaction. That's why I've got reaction down there. Obviously, in a chemical change, you have a new substance formed. That's the biggest difference. It's a brand new thing formed. And the biggest thing here, what we're going to see, and I'm going to relate to this in the next period. I'm going to give you a chance to do some problems in between, some questions, is that you have a new arrangement of atoms in your chemical change, even though there are no new atoms formed. I'm going to leave that up there, I want you to really keep that one statement in mind because I'm going to write on the board over here multiple examples of this. In the next period. That won't make sense to you quite yet. It will when I do my examples in a little bit. But what I'm saying, I guess I could probably use one example, maybe something that I'm not going to do in the next examples here. Let me just use something I'm not going to do. We talked about water, right? I can take water, right, and I can boil it. I said that was a physical change. But what if I took water? And I can do this. I'm actually going to do this. Not tomorrow. I'm going to do it much later in the year. There's a piece of equipment back there that I can pass electricity through water. And I will get on one side a gas and on the other side a different gas. What do you think water, when I don't do this, don't write this down. If I were to do a chemical change, what do you think water breaks up into? What do you think? If I can pass electricity through it. Well, if I just boil it, it's still water. But if I pass electricity and break it down, you know what I'll get? I'll just get two elements. What are those two elements? Hydrogen gas and oxygen gas. Now, the way you write that, you're going to learn. I don't do this till later because you don't know about diatomic elements. You have to write them like this. You don't know how to balance equations. You'd have to balance them with a 2 there and a 2 there. That's all coming later in the year. But the point is, notice there's a new arrangement of atoms. Okay, they're not bound the same way they were. However, there are no new atoms. If I've got H's over there, how many H's are on that side right now? 2 times 2, 4. How many are here? 4. How many O's are over there? 2. 2 over here. Okay, that's something that's beyond you right now because we haven't done equations. We haven't done any of these different kinds of reactions. But the point is, and you're going to see the same point with my examples in the next period, I have rearranged, I've mixed them up, I've done different things with them, but I haven't created or destroyed them because that would violate yesterday's law of conservation of matter and energy. Okay. All right, so lastly then, for chemical changes, I want to remind you that anything your body does, anything a living thing does, is going to be a chemical change. All biological functions. So think about that. Specifically, for chemical changes, you don't know about a lot of them. Like I said, you're going to do a ton of them throughout the year. But for this first chapter, you should be familiar with anything that's associated with you or a living thing. So, if I talk about digestion of food or healing of a wound, clotting of blood, all right, taste, smell, anything your body does is a chemical change. Not a physical change. Okay, that's very important you understand that. There are chemical reactions going on in your body all the time. All right? Okay, now, the homework, I believe I have up here, yeah. Copy those down. That's not up there yet, I don't think. No. And copy those down. And you can have the rest of this period, because there's not that much time left, to do these and the ones before it. And then we'll do the next half. We have some more demos.